So in this part, we will be talking about light emitting diodes, diodes that can emit light at a particular wavelength depending on how much voltage you apply across them. So that's light emitting diode. Earlier, we were talking about diodes, like the small signal diode over here that you see, 1N4148. We have been doing all our experiments using that. That was a small signal diode that was primarily used for a fast switching application. We also used that for doing a voltage limiter. We also used it for voltage rectifier. But there are other other diodes over here. This is not a diode. I should probably take this out. That's a phototransistor. Um, there's a red, green, and yellow LED that you can see, and there is a Zener diode. That's the element right there in the blue casing. So Zener diode, we are going to talk about that in the later half of this. Um, but LEDs are right now what we are dealing with. So I'm going to move these components by the side here and talk about these three. So what happens when I take a red LED, for example, and I have a long lead and a short lead here. So the current is only going to be flowing from the positive to the negative side. So it has the polarity the same way as our diodes from earlier. And when I apply a certain voltage across this LED, it is going to turn on. And depending on how much current flows through this uh, diode, it is either going to be a very dim light, or if there is a lot of current that is flowing through the LED, the brightness can be very high. So it can have a dim versus very bright light output, and that would depend on how much current is flowing through it. But we should be careful with the LEDs. We can actually damage them if we apply too much voltage across them. So for example, if we say do not have any resistor in our circuit, it's a very bad idea to do that. But if suppose we don't have any resistor in our circuit and we simply connect a voltage supply to the two ends of the LED, depending on how much voltage we connect, we might actually damage the damage the LED. So we don't want to do that. We want to have a resistor in series with the LEDs so that we are able to limit the current that goes through, and the voltage whatever we give is essentially split between those two components, a resistor and the diode. So in all our experiments you will see a resistor in the circuit that will help us protect our circuit elements. Now what is the difference between these three diodes? Are just the color of the plastic casing is different? Uh, no, their threshold voltages are different. So, for example, for a red LED, we would need about 2.2 volts to turn that on. For a green LED, we might need a larger voltage to turn that on. So it might go from 2.2 all the way to 4 volts to turn a green LED on. And for a blue LED, it will vary between 3.5 and 4 volts. All these details are provided in the write-up, so I encourage you to read that. But in the middle of the screen, you should be able to see an equation. And that equation allows you to determine the current through the diode, the LED. So I'm going to quickly sketch up something to see what that corresponds to. So for example, if I have a voltage source, I'm connecting it to a resistor and I'm connecting it to say an LED. This is ground, this is an LED, this is my voltage source, and let's call this V in, this is R. So clearly we would need some VLED, that's the threshold voltage for the LED to turn on, then we are essentially using this equation to find out what is the current that will flow through the circuit. Um, and as you can see, there's a simple voltage divider happening here. Vin, our supply voltage, is being divided between this resistor R and the LED. And the LED or the diode will have a limiting effect on the positive voltages over here. So if suppose we use VLED as our voltage that is limiting, then voltage across this resistor will be Vin minus VLED. So that's the numerator over there. And then if I divide that with ILED, that is going to give me what ILED is the current that is allowed to flow through the resistor and through the LED, which is typically a value of about 20 milliamps. 20 milliamps is a good current to shoot for. So if you want this to be 20 milliamps, the current through our LED, then we can adjust the resistor R such that we only allow 20 milliamps to flow through this. And that's how we calculate the value of R to be used in our circuit. And there is so the simple voltage divider, and that's it. All of this is described in the write-up, and I encourage you guys to read it. Let's see. Now, so that's as far as LED is concerned. So they emit red versus green versus yellow wavelength light depending on what kind of threshold voltage they operate at. So their doping is different. So it's not necessarily the plastic casing, it is the doping of those materials that is making it different, which makes it respond to different threshold voltages and emits a different wavelength. Okay, that's as far as LEDs are concerned. If I go down, I have photodiodes, which is a light sensing component. We don't have photodiodes as a part of this class, but the theory about that is given to you. And this is essential. And if you look at a photodiode, it looks very similar to an LED. The only difference that you might observe is that the casing will be completely black. So instead of having a color like red, green, and yellow, for photodiodes, the casing will be completely dark black. And for a phototransistor, which is what we have over here, the casing is transparent. So phototransistors is what we are going to use for EI to detect light. Photodiodes could also be used to detect light, and essentially they allow current to pass through them when there is light, ambient light that falls on them. Um, Again, please read the statement. Please read this paragraph to get a sense of what they do. Essentially, I'm going to allow current when light falls on it. That's essentially what they're doing. Phototransistors, however, have a little bit more use. And the reason why phototransistors are slightly better is because the current that flows through the transistor when there is light falling on it can be amplified. And as you know, the transistor operates in three regions: the cutoff region, active region, and the saturation region. If we are able to operate that transistor in an active region where it functions as a current amplifier with a gain of around 170 that we explored in experiment 6, we can get a large amount of current or photocurrent to flow through our phototransistor. So as you can see on this graph here, both X and Y are on a semi-log scale. On the x-axis, we have the radiant incident, so that's the intensity of the light that is falling on the phototransistor. And on the y-axis, we have photocurrent. So as you can see, more light, more current will flow through. And if we can place a resistor in our circuit along with the phototransistor, all that photocurrent will go through the resistor which means that the voltage being measured across that resistor will increase linearly as we increase the amount of light that falls on it. And if we were in class, I would show you how you could have used say for example your iPhone. uh, the new iPhones, or actually any phone right now, you can calibrate the amount of light that comes out of it. So you can go in stages of 1, 2, 3, 4, and as you increase that linearly, you can increase the photocurrent that goes through the phototransistor. So same application, sense light, but now the amount of current that is going to flow through as a result, which is the photocurrent, is going to be of very high value. So which means that it is going to be easily detectable. So in this experiment that is going to follow, we are going to use LED to generate light, and we are going to use phototransistor to detect light. And the experiment that I'm talking about is written up right here. So we are going to use this LED, and we can choose any LED. We will take the red one. So we are going to place this LED right here. Let me zoom in. We have wave gen connected to a resistor, and I talked about why we need this resistor, so as to protect this LED and not accidentally increase this wave gen to a higher value and have a damaging effect on the LED. We have this resistor there, 330 ohms, so that's orange, brown, red LED, and on the negative side we have -5 power supply that is connected so that we can explore a bigger range of voltages on the receiver. So this is our essentially a separate circuit. This is going to be our optical transmitter, if you will. And then we are going to transmit light, and on a separate circuit board we are going to place a phototransistor where the base of the transistor, earlier we were controlling the base of the transistor by using a base voltage with respect to the emitter. Right now our light is essentially functioning as our base voltage. So when there is light, there is going to be current that flows through. When there is no light, then the phototransistor will not allow any current to flow through, and that photocurrent will be linear. It will be the same current that flows through R3, and we can measure the voltage across the phototransistor or measure the voltage across R3. In this case, what is going to happen? Well, when there is light, let's see, light, uh, when there is light, then the phototransistor is on, which means voltage measured on channel 2, say channel 2, should be around 0, because now the phototransistor is allowing current to pass through. It is essentially shorting out the not shorting out, it is connecting collector and emitter pins together. So it's effectively like there is a short circuit between those two terminals when there is light. When there is no light, the phototransistor is off, which means that the voltage across channel 2 will be a high voltage, whatever, very close to whatever you measure on V plus. A little bit smaller than that, because if you have a measurement here, that means that this is going to be 1 mega ohm. That's our input impedance of our analog discovery, and V plus is 5 volts, say. It is going to be split up between 56 kilo ohms and 1 meg. So it's going to be slightly smaller, and we are measuring across that 1 meg resistor. So it's going to be slightly smaller than 5 volts. So as there is light and no light, the output measurement should go up and down compared between 0 and something close to 5 volts. And that's exactly what we will observe in the experiment that we are going to conduct shortly. So I'm going to place all of this on one board, and I'm going to place all of this on another board, two different boards here, and they are only going to communicate with each other using light. So that's what we are going to do. So let me place this by the side here. Actually erase this so that we can see things better. I'm going to move my LEDs to the side, and I'm going to bring in two boards. Okay, it's going to be a little bit tricky, but let's see what happens. All right, so I have two boards here. Actually, let me connect them together. All right, so I have two boards. On one board, I have a 330 ohm resistor. So that's my 330 ohm resistor right there. And the other end of this resistor is connected to a red LED. The positive terminal is there, negative terminal is at the bottom, which is connected to this rail, which is connected to the white wire, where I'm going to provide negative 5 volts. I have connected wave gen on this side, and I'm measuring wave gen as well. So I've connected, that functions as my transmitter board. On this side, I have a 56 kilo ohm resistor, which is a green, blue, orange color code. And then I'm going to place the phototransistor right there. And the thing that you have to be careful of with the phototransistor is that there is an orientation to this, which is a little bit difficult to see. So if you look at the phototransistor from the top, there's that plastic casing will have a flat edge on one of its terminals, which is the collector. So that's going to be towards the resistor there. So I'm going to disconnect the boards again. Okay, that's pretty good. And then place my phototransistor right here. So on one side, I have connected my LED on the left side, and I've turned the leads in such a way that the nose of the LED is pointing right. And similarly, on the board to my right, I have placed a phototransistor with its nose facing the LED, so that there is good coupling of light when I close them close to each other, place them close to each other, and then as I separate them out, the coupling of light from the LED to the phototransistor is going to be weak. So let's see how this all plays out. I'm going to start my so let's see, I still have a few more connections to make. So for example, I need to make a connection of red wire. So I bring in my red wire here to that, and let's see, square wave with a frequency of 100 hertz. V minus and V plus are supposed to be both 5 and negative 5. So I'm going to go back to my waveforms window, going to wave gen. I also need supplies. So both of them need to be at plus 5 and minus 5. Oh, and then I'm going to turn that on. Going to go to wave gen, make that into a square wave. 100 hertz is okay. Amplitude is 5. Yes. Turn that on and go to scope. Before I start scope, what I'll do is I will switch off the light here so that you can only see the LED. So as you can see, the LED is on and it is blinking very fast at the speed of 100 hertz. And I know it is blinking because I have switched on the wave gen. In fact, if I go down to say 20 hertz, then I can see it blinking better. And if I go even further down, so for example 5 hertz, then I can see it blinking very clearly. So I'm going to go back up to 100 hertz so that to the human eye it appears like it is on all the time. However, in reality it is blinking very fast at the rate 100 hertz. So supplies are on, wavegen is on. So let's go to scope now, where my channel 1 is measuring the wavegen and channel 2 is measuring the voltage across the phototransistor. So if I turn on the scope, let's see, I have let me bring them down so that we can see better. And on the blue guy, let's say 1 volt is fine. Offset, I can make offset -2 and -2. Perhaps range should be set to 2 volts per division. So now they are both consistent. So as you can see, when there is light indicated by a high voltage on the wavegen, we measure very small voltages on the output like we established in theory. And when we have a low voltage at the wavegen, we measure something that is high. It is close to about 5 volts here, as you can see. And I can increase that, make it better coupling versus very bad coupling. And as you can see, my room is so dark that I'm not really seeing a big change here. But if you did this in a room where there was ambient light, you would be seeing a lot of noise. In the signal would not be quite that good. And I can show that, you know, I can block the light in the middle by placing say for example I can put a piece of paper in the middle, and that will essentially block the light. So if I block the light, as you can see, the output goes up, and if I remove the paper, it comes down. Because when I block the light, the phototransistor is going to be off. Even then, some of the light is getting through. And if the phototransistor is off, that means that I'm going to be measuring a high voltage. All right, so I hope that was a good demonstration there. For the phototransistor, I will be providing all these plots, of course, for you to use. As you can see, I'm able to move these two boards quite far from each other and still be able to measure very well. So that goes on to show that I have done a pretty good job in terms of isolating them. In terms of getting the room to be dark. So if I go all the way over here, I'm still doing a pretty good job there. Okay, so what I'll do is, so clearly if I put them, you know, not facing each other, then I don't have any coupling there. But I bring it close to each other, then I have really good coupling there. Okay, I'm going to switch off supplies, switch off wavegen, switch off scope. Then look at the time. It's 9:40. So I'm going to look at what are the remaining things we have. Um, so we talked about observing the output. We played with that a little bit. Um, we I can provide you with all the plots, but I hope now how you can see how to build this. Let's see. The last thing that we have on the yes, Zener voltage. Yes. So for Zener, we have 10 minutes. I'm just going to give you a sort of a quick discussion on Zener, but when we come back on Thursday, we will go a lot in detail. So I'll point out the key differences between the earlier diodes and the Zener diode. So if you start with the symbol itself, the symbol of the diode, the Zener diode, will have those limiting sort of indicating that there is voltage regulation happening. So instead of a flat line, it is curved. And a Zener diode is similar to a diode. However, the key difference is that it breaks down at a very uh, convenient voltage. So for a normal 1N4148 diode, the small signal diode, our reverse breakdown voltage was around negative 100 volts. However, for a Zener diode, we might break down around negative 5 volts or negative 3.3 volts or negative 1.25 volts or around negative 10 volts. Something that is quite desirable for circuit designers to use as voltage regulation. So the voltage regulation is even if there is a small change in current, my voltage between 2 points should not change. And I can use Zener diode in reverse bias to get that voltage regulation to happen. And that voltage regulation typically happens around negative 5 or negative 3.3 volts depending on your circuit application. So that's the voltage current characteristic of a Zener diode. On the forward bias, it is exactly the same. And as you get into the reverse bias situation, reverse bias region for the diode, it is the same. However, when you go around this Zener voltage, which is around negative 5, it breaks down around that region because of how the doping and the construction of the diode is happening. Now, for a normal diode, it happens at negative 100, but negative 100 is not a typical value where I would need voltage regulation to happen. And 0.7 is also not a typical value that I would need regulation to happen. I need certain voltage like negative 5 where I would need voltage regulation, and all safe circuit designers will have a voltage regulator on their circuit board. It might appear in the form of a Zener diode or it might appear in the form of a separate voltage regulation IC. Over here we are going to see how we can use Zener diode for the application of voltage regulation. So on the positive side, it cannot go beyond 0.7. On the negative side, it cannot go lower than the Zener voltage, typically one of these values. So we'll explore that in a PSPI simulation, and we also explore that experimentally. So the key is the Zener diode might look very similar to the normal diode except for its reverse breakdown voltage, because that's an application for voltage regulation. So on page number 17, you have most of the things are for capture PSPICE simulation, but there is some hardware exercises to be done, and we will do that on Thursday when we meet next. So if we are able to complete that will finish experiment 8. So that's a small part that's left for Thursday. Okay, so I think for today, that is going to be it. I will stop the recording and see if you have any questions.